Okay, it's 3:35. Let's get started into a new chapter about distributed training. So we have gone through two chapters already. The first one, we talk about efficient inference techniques, pruning, quantization, distillation, teacher-student model, etc. And the second part is about domain-specific optimizations, such as large language model and transformers, vision transformers, the GAN models, video models, point cloud models, and also the diffusion models, right? So now we are going to switch gear to talk about the third chapter of this whole course, from inference to training. How do we train those large-scale models fast on multiple GPUs? In the after the next lecture, we're going to show you the real-world training infrastructure. I'll give you a lab tour into the basement where we have lots of servers, give you an idea what does it look like. So we are going to have 4 lectures related to training. 2 lectures about distributed training on the cloud, and 2 lectures about how to do on-device training to be able to fine-tune your model locally on your edge device. So let's now start with the first part, which is distributed training on the cloud. And here is the lecture plan for today. It's pretty dense, a lot of cool knowledge, starting with the background. And we'll talk about 3 parallelization methods in the high level: data parallelism, pipeline parallelism, and also tensor parallelism. Next, we're going to focus on the data parallelism, and then talk about the communication primitives. How do we communicate between different GPUs and different nodes? In particular, recently, with the advancement of large language models are getting super big. How do we further reduce the memory in data parallelism? We're going to introduce 0, 103, and also FSDP, fully sharded data parallelization. Next, pipeline parallelism, and then tensor parallelism. After taking today's lecture, you will know how to train a super big model in limited GPU memory. So let's start with the background and motivation. Why do we need distributed training? So models are getting larger. In order to get good accuracy, model size is pretty big. The compute is also pretty big. And recently, the large language model is really driving up the demand for compute, hundreds of millions of parameters with a lot of GPU hours to train. According to this data, we want to train Ryzen 50, that takes about 31 GPU hours with about 26 million parameters. For base, 100 million parameters in about 84 days. The GPT-3 175 billion parameter has huge amount of parameters, and it takes about 355 years to finish on a single GPU, which is enormous. So there's a interesting part. The boss is asking, what did you do over the last month? I trained the model for 1 epoch. What's your plan for the next month? Train the model for 1 more epoch. So the training time is greatly limiting the productivity for machine learning researchers to design new models. So how do we make it faster? Just use more GPUs. So if training takes over single training takes a single GPU 10 days, 10 GPU days. If we can parallelize with 1,000 GPU, right? Assume linear scalability, that takes only 14 minutes, like over a cup of coffee. So it can greatly accelerate our design cycle to train these large-scale models. So let's see a real use case for distributed training using thousands of GPUs in our lab. So we've been using this Summit supercomputer. This is how it looks like. It was roughly in 2018-19. So we still have 6 V100 GPUs, which was actually two generations behind. Now we have A100 and then H100. And they are having the EDR InfiniBand. EDR was 200. It's still real, so it's 200 gigabit per second. Now I believe we can easily get 400 gigabit per second InfiniBand. So we are training this video model called the temporal shift module, which we introduced last week. on one node with 6 GPUs takes almost 2 days, 49 hours, and this accuracy. We scaled up to 1,536 GPUs, and really it just takes 14 minutes to 100 times faster. Okay? We can reduce the training time from 2 days to 14 minutes, and that's actually something really doable over a cup of coffee. Training this 8-frame Ryzen 50 temperature shift module to understand the videos using this kinetics dataset. So hopefully that gives us enough motivation. Why do we need distributed training? And now let's dive deeper into what are the parallelization approaches, parallelization opportunities to distribute the workload among multiple nodes. We're going to introduce 3 kinds of parallelism: data parallelism, pipeline parallelism, and also the tensor parallelism. So data parallelism is saying that we have 3 multiple GPUs, okay, in yellow, in blue, in green, in red, and they share the same model. They have the same copy of the model, but different copy of the data. You have the blue data, you have the green data, you have the orange data, and then you distribute the green data to GPU 1, blue data to GPU 1, the green data to GPU 2, and the yellow data to GPU 3. Okay, so they're sharing the model, they're using different pieces of data. Okay, so this using the same model across different devices. The second part is the pipeline parallelism. Okay, so rather than dividing the data, now we are going to divide using a single copy of data, but divide different parts of the model across different GPUs. Okay, so the first part of the model, we deploy it to GPU 1. And the second part of the model, second layer, for example, we deploy to GPU 2, etc. The last part we deploy to GPU N. A third way of doing parallelization is using tensor parallelism. So what does that look like? Again, we have a training data, we have a machine learning model. Now we wanna, for each layer, okay? So for each layer, we deploy a different part of the tensor, like 1/3 of the channel, 2/3 of the channel, the last third of the channel to 3 GPUs. So even for just one single layer, a single matrix multiplication, that is done by multiple GPUs. So we can do it for the first layer, we can do the same for the second layer. Okay, so divide each layer, each matrix multiplication, each convolution across multiple GPUs. But here we're using the same piece of data. Okay, and then we are going to dive deeper into each of the parallelization opportunity and to see what is the challenge, what is the benefit, pros and cons for each approach, and when should we use data parallelism, when should we use pipeline parallelism, and when should we use the tensor parallelism. So now let's start to dive deeper into the data parallelism. So this is a basic high-level idea about data parallelism. We have a single parameter server, which is a central controller of the whole training process. And here we have 4 workers. And each worker can be a GPU, can be a node. And they are, each GPU, each node has the data associated with it. So we call it workers, which compute the gradient using a splitted data set and send it to the delta W, which is the gradient, to the parameter server. The parameter server receives those gradients from multiple GPUs, from the multiple workers, and send back the updated gradients. Okay, since they have different copies of the gradient, the parameter server will aggregate them together and update the weight and send back the weight to multiple workers. So let's see how that works. We have a parameter server, and then we have a pool of workers. So the parameter server has a neural network model and also the gradient. So you first replicate the model weights among multiple workers. And here we have 4 workers, okay, 4 workers, replicate the weight. And then each worker will use part of the splitted data set. Okay? They're using part 1, part 2, part 3, part 4 of the training data, using the same model to do forward and backward. to calculate the gradient. Are the gradients the same? No, the gradient's dimension is the same, which is the weight dimension, but the value is different. Why is that? They are trained on different copies, different split of the training data. Therefore, the local gradients are of the same dimension, but of different value. So you train the model using your split of the data on your local copy and to get the local gradient. Then different worker pushes their local gradient to the parameter server. So sum them up to get the sum of all the gradients. And the parameter server use the sum of the gradient to update the model weights. And after the model update, it will repeat the process by putting each worker putting the updated weight from the parameter server to its local replica of the neural network model so that they can stay synchronized. Everyone has exactly the same copy. So that's basically how data parallelism works. They have the same model, but they have different data. And this is the big picture about the 5 steps: replicate and pool, and then split the data set, and the second step. And then the third step is compute the local gradients and push it to the parameter server and update the master model weights. So compared with the single node training, where for many different iterations, we sample the data, compute the gradients, and then do a step update. Here, we want to insert 2 more steps. Okay, they have to be synchronized. One is to replicate and pool the gradients from the parameter server, and then each node compute the forward and backward to get the gradient, and finally push its local gradient to the parameter server. And here they have to stay synchronized before the master parameter server is going to do the parameter update. So now let's talk about communication primitives. Since we have to communicate among different nodes, what are the different methods we can communicate? So the first one is one-to-one communication. Okay, so there's 4 nodes in this example. One-to-one communication is just directly transfer from one node to another. Send and receive are the most common used distributed communication schemes implemented in socket, MPI, glue, NCCL, etc. Just individual node from 0 to 3, from 3 to 0, send and receive. So that's one-to-one. There's also the one-to-many. Okay? So you have one node, you have 4 pieces of data: the green one, yellow one, blue one, red one. And the scatter is basically saying send the first one to node 0, the second one to node 1, third one to node 2, the last one to node 3. So this is one-to-many communication. One initiates the communication, and then it gets broadcasted, gets scattered to many different workers. And gather is saying each worker has a separate copy of one part of the data, and it's going to gather it together in another node. So which is the inverse of the scatter process. And very similar to gather, we have this reduce function. Okay, so if you compare reduce and gather, what is the difference between reduce and gather? So first of all, it's also a one-to-many communication. Similar to gather, you have multiple nodes, you put it together. But here, you not just have them in an array separately, but now you want to average or sum, basically reduce them together into a single value. Sum is probably one of the most commonly used reduction function. Compare and gather and reduce, for example, you have 1, 2, 3, 4. the gathered result will be an array with 1, 2, 3, 4. But the reduced result will be summing them up together with a single value. It's 10. It's a single scalar value rather than 4 separate values. And then we have this broadcast, just the same value, like in green, and then we send it to all the workers. So all the workers have exactly the same copy. So that's broadcast. So we talk about one-to-one, one-to-many. Now there's also the many-to-many. So here we have 4 workers, we have another 4 workers. All reduce is basically saying that not only reduce on one node, we'll collect all the nodes' results and reduce them by summing them up. Now every worker has to do the same. Worker node 0, worker 1, worker 2, and 3 all have to repeat this reduce process. That's why we call it all reduce. All the nodes want to do this reduction operation. Since we talk about the difference between reduce and gather, we can easily understand all gather. Okay? So each node will gather the information from node 0 to 3, and all the nodes want to repeat the same process. That's why we call it all gather. So the difference between one-to-many and many-to-many is basically you want to process either reduce or gather on all the workers. So let's put that in the context of parameter server and also data parallelism to see what is the communication, where is the communication primitives, how did they get used into the data parallelization. So remember, we have replicate process to for each worker to pull the weights from the parameter server. We also have the process of the push process where each worker calculates its own copy of the gradient and you want to push it and sum it in the parameter server. So which type of communication scheme is used in replicate and pull and also push and sum? So here, replicate and pull, basically we have a centralized copy of the weight. Okay, so it's one-to-many. Okay, it's actually using broadcast, the same piece of activation from a centralized parameter server. We want to broadcast it to all the workers. So we are using broadcast to broadcast information, the weights from the parameter server to all the workers. What about push and sum? Each worker has its own copy of the gradient. And we want to have a many-to-one operation so that we want to sum them up in the parameter server. So we are using the reduce primitive to average all the workers' gradients and put it in the parameter server. And what is the bandwidth requirement for each node? There are 2 types of node. One is the parameter server, which is centralized parameter server. The other are the worker node. So we can talk about the worker node and also the parameter server node separately. First of all, for the replicate and pull process, okay, for the worker, everyone just pull one copy, so it's O1, but the parameter server has to serve n workers at the same time. So the workload, the bandwidth requirement for the parameter server is On, worker is O1. And similarly for the push and sum, each worker just push one copy, but the parameter server has to receive n copies since we have n workers. That's why the worker node has O1 complexity, while the parameter server has On complexity. So what's the problem here? Not scalable. As n gets larger, n is the number of worker node, the traffic in the parameter server will get pretty heavy, right? So this method is not quite scalable. We want to get rid of such On complexity. where the bandwidth for the central parameter server grows linearly with the number of workers, which can easily become the bottleneck when the number of workers gets larger. And do we have better approaches that's more scalable using a decentralized manner? We can actually use all reduce. And let's see how that works. Now we no longer have a centralized parameter server. Everyone is the same. So all reduce is basically saying we have to do the reduce process for all the workers. Now we have 4 workers, so we have 4 steps. Step 1, we do reduce on node 0. It collects the information, the gradient from node 0, 1, 2, 3, okay, and sum them up together by itself. In the second step, we do the reduce for the second node, node 1. That's why here the pseudocode is basically looping through all the node 0, 1, 2, 3, and each time we do all reduce for work I. So here the time is basically On, since we have to do it for each node, and the bandwidth requirement is also On, since each time we have to communicate between n nodes. We can do another approach, which is basically using the ring or reduce. So ring or reduce is saying that we only communicate with my direct neighbor, my left and right neighbor, rather than communicate with all the all the other nodes. So step 1, node 0 send its information to node 1. Node 1 send its information to node 2. Node 2 send to 3, 3 send to 1. And after that, node 1 will have the information both from itself and also from its previous neighbor, node 3. Similar for node 1 has both yellow and also green. And step 2, we repeat this process, 0 send to 1, 1 send to 2, 2 send to 3. So after that, each node will have 3 neighbors copy, not only itself, but also its direct neighbor and neighbor before that, indirect neighbor by 1 step. And finally, we do one more step, 0 to 1, 1 to 2, 2 to 3. So now you have 4 nodes, everyone's information. Your previous node, your previous node, and the node even before that. So here, from iteration 0 to n, I send it from I to I plus 1, modulo by n, and everyone receive from I plus 1 modulo by n. And worker will merge the information that it newly receives. So again, you need to repeat proportionally the number of steps proportionally to the number of nodes. But the bandwidth requirement is O1, since each time in the network you only talk to your neighbor. So the bandwidth is reduced, and each step you just perform a single send and merge with your neighbor. So this is a very commonly used approach for distributed training using ring or reduce. Can we do it in parallel? So previously, when we talk about all reduce, we repeated for each node by node, like reduce from node 0, reduce for node 1. Can we do them in parallel? Certainly, we can do that. At the same time step, since they have no dependency, I can do the reduction for 0 in parallel with reduction for node 1, as long as you have enough bandwidth. So the bandwidth requirement in this case will be On square, since each node required to talk to all the node, and you have n of them. That's why you have On square bandwidth requirement, which is actually worse. But what it buys you is basically to shorten the time to O1, since everything happens in the same cycle. So this is comparison among different distributed aggregation methods using parameter server. The time is O1, but unfortunately, the peak node bandwidth is On due to the centralized parameter server, which is not quite scalable. And total bandwidth is O(n) because every node has to talk to the parameter server, and there are n such nodes. All reduce, if you do them sequentially versus parallelly, they're different. If you do them sequentially, time is O(n), so you have to do the reduce for each node, versus do them in parallel, you can do them in just the same cycle. While the requirement for the bandwidth is different. This should be O(n) square, and can make an edit here. It should be O(n) square here. And here, if you do them in serial, the peak node bandwidth is only O(n). Oh, actually, here is the peak node bandwidth versus the total bandwidth. Actually, this is correct. The total bandwidth is O(n) square, and the peak bandwidth for each node is still O(n). Or you can do the all reduce, the ring all reduce function where you only talk to your neighbor. So the time complexity is O(n), so you have to repeat this process for n times to form a cycle. But the node bandwidth is O(1), since you only have to talk to your neighbor. So let's see, do we have some more advanced technique? Actually, there's a new technique called recursive halving or reduce. What it says is that in this case, we have 8 nodes. Can we do some tree structure to have some log time complexity? Actually, we can achieve that. In the first step, each node exchange information with its neighbors offset by 1. So 0 and 1 and 2 exchange information with each other. So both of them has each other's information, green and red. And 3 talk to 4, 5 talk to 6, mingle the color, 7 talk to 8. And next time, what do we do? What do we do here? Offset of 2. Each node exchange with neighbors with offset 2. So 1 talks to 3, 2 talks to 4. So that's among these 4 nodes. 5 talks to 7, and 6 talks to 8. So that's about these 4 nodes. It's like getting lookalike tree. And then we have the information. Node 1 now has the information among all 4 nodes, since part of this come from node 3, part of it come from the previous iteration. Similarly, for node 5, 6, 7, 8, they all have the information of each other. Then we just need one more step to exchange information with neighbors of offset 4, where node 1 talk to node 5. Okay? So combining them all, you will have all the information. And node 2 talk to node 6, so it will combine all the information. Node 3 talk to node 7, and node 4 talk to node 8. Therefore, each node has everybody's information in only log n number of steps. Here, n is 8, but we need only 3 steps. Neighbor, offset 1, offset 2, offset 4. So for n workers, all reduce can finish actually in log n steps if we use this recursive halving or reduce. Okay, so these are some of the communication primitives that can scale to a larger amount of workers, since this is just using log n complexity. And next, let's talk about how do we further reduce the memory in data parallelism. Actually, this is the bulk of the discussion today, especially in the context of large language model, which can get super big. And we're going to discuss the fully sharded data parallelism. So we can have multiple GPUs. Each GPU handle different pieces of data. This is data piece 1, piece 2, piece of. Although the parallelism can reduce the amount of data, but here you can see the GPT-3 has 175 billion parameters. Each of them is 2 bytes. If using IP16, that requires 350 gigabytes of memory. And actually, during training, you not only have to fit these model parameters, but you have the gradient. And what else do we need to have during training? What else do we need to store in the GPU memory? Is that enough? Actually, this is far less, not enough by far. You have to store the optimizer states. If you use Atom optimizer, how many bytes do you need to store the optimizer states? You need to store 2 floating point numbers. Each of them is 4 bytes, FP32, so that's 8 bytes. And if you do FP16 training, you have to store a master copy, the FP32 master copy, although you are using FP16. So actually, there's a lot more than the weight itself. So A100 GPU has only 80 gigabytes of memory. So even the best GPU cannot fit the model weights into memory. And also we need to store the gradients and also the optimizer states, which further exaggerated this problem. So let's visit the DeepSpeed proposed a series of methods to distribute the weight, the optimizer state, and also the gradient among multiple GPU workers. So let's see how that works. To apply apply DeepSpeed 0 to distribute training. So here we show we have a large number of GPUs, and we have different components, the weight, the gradient, and also the optimizer states. By default, we use FP16 mixed precision training. So since it's FP16, the weight occupies 2 bytes in blue. And the gradient also occupies 2 bytes in blue. The tensor dimension of the gradient should be exactly the same as the weight. What about the optimizer state? So optimizer state depends on the optimizer that you use. A commonly used optimizer is the Atom optimizer, which has the momentum and also the variance. And that requires to be stored in FP32. You also have to store a FP32 master copy of the weight. To add them together, you have 4 bytes plus 4 bytes plus 4 bytes. You have 12 bytes. So those 12 bytes are shown in green. It's actually much larger than the weight and gradient itself. So in order to train just one single parameter, you need 2 plus 2 plus 12. Okay, it's actually 16 bytes to 2 bytes for the weight in FP16, 2 bytes for the gradient in FP16, and also 12 bytes for the optimization states. So let's see how many parameters can we fit to train on an 80 gigabyte A100 GPU. Since training each parameter requires this amount of bytes, that's 16 bytes. If we have 80 gigabytes divided by 16, actually we can only train a 5 billion parameter model in this way, which is far less than the state of the art, which is 175 billion parameter model. Maybe this has already been exceeded, surpassed. So how do we deal with it? Apparently, we can see the bulk of this part is occupied by the optimizer state. And here we can actually do algorithm and hardware and system co-design. On the algorithm side, we can reduce the number here. Okay, rather than 2 plus 2 plus 12, can we reduce this 12? Can we reduce this 2 and this 2 here? Remember when we talk about LoRa, we talk about using low precision to represent the weight. We can also use low precision for the gradient during training, which we are going to cover in the on-device training lecture. So on-device training and cloud training are not necessarily apart from each other. Lots of the techniques can actually be shared, for example, using lower precision for training. And especially the biggest part is actually the optimizer state. Okay, so among 3 numbers, 1/3 comes from the IP32 copy of the parameter, and 2/3 comes from the optimizer state, which is momentum and variance. So people can develop, we can try to develop some new optimizers that require less optimizer state. So there's research like Lion that will only use 4 bytes rather than 8 bytes for the optimizer state. So since the optimizer state is occupying the most of the memory, we can shard the optimizer state. Shard just means partition. Okay? Partition the optimizer state across different workers. For example, worker 1 only has its own copy, part of the optimizer state. Therefore, it can only update its own copy of the gradient and also the weight, because it only has its own copy of the optimizer state. What if it want to access to others' optimizer state or weight? You can just exchange the information by the communication. So in this way, in 0, 1, propose to partition shard the optimizer state so that we can divide the optimizer state by n, so that you can reduce the number of bytes for each parameter. So 2 plus 2, if we assume having 64 workers, so 12 divided by 64 plus 4, you have 4.2 bytes to train each parameter. So you divide 80 by 4.2, you can train a 19 billion parameter model. What parameter can we train before? Only 5. Now it's a big improvement, okay? From 5 to 19. Can we do better? What else can we shard? We can also continue to shard the gradients. So rather than having all the gradients, you only have your own gradient, and you are responsible for updating your own weights. So in this way, we further divide the gradient by n. Previously, we have 2 bytes for each parameter. Now we have 2 by n divided by n for each parameter. Assume again for 64 node, we have 2 plus 2 divided by 64 plus 12 divided by 64. So that's only 2.2 bytes per node. So if we divide 80 gigabytes by 2.2, we can fit a 36 billion parameter model. It's even better, almost doubled than the 0, 1. So from 0, 1 to 0, 2, we not only shard the optimizer states, but also we shard the gradients. So in practice, 0, 2 is a lot more widely used than 0, 1. So you have almost a free lunch to fit larger model in the GPU. So naturally, we can continue to shard more, even shard the weight. But this makes it a little harder because during inference, you don't have all the parameters for inference. In backpropagation, you have to first do a forward pass and then the backward pass. Both of them require to have access to all the weights. So actually, you have to communicate to receive the weights, to gather the weights, to gather the weights from other GPUs so that you can do a complete forward and backward. But fortunately, in this way, we can also shard. So everything here, the weight, gradient, the optimizer state will be divided by n. Assume n is 64. Again, in our example, each node requires only 0.25 bytes of data. So in an 80 gigabyte of GPU, we can now fit 330 billion parameter model. So from 36 billion, now we can do 320 billion parameter. So what's the trade-off here? We need to communicate more. Okay, the more we communicate, the less we need to store. When we need something, when we need the weight, we just do a gather from other servers. Okay, so that's why it's getting super important to use high-speed interconnect like InfiniBand in a modern infrastructure of distributed training. When we do the lab tour, I will show you how it looks like for those InfiniBand infrastructure. So now let's put them together to talk about this data parallelism using 0, 1, 0, 2, and 0, 3. 0, 1 shard the optimizer state. 0, 2 also shard the gradient. And 0, 3 also shard the weight. And the model size it can fit in a single GPU, just keep increasing. And since 0, 3 can fit the largest model, people give it a name in PyTorch, implemented in fully sharded data parallel. A fully sharded means everything is sharded, not only the optimizer state, but also the gradient and also the weight. Everything is sharded, fully sharded data parallel. Okay, fully sharded data parallel as FSDP. And this is very commonly used, very useful in training large language models. All right, let's now take a break before we talk about pipeline parallelism and also tensor parallelism. All right, welcome back. After talking about FSDP, fully sharded data parallel, let's conclude the data parallelism and introduce two more parallelization opportunities. One is the pipeline parallelism, and the other is the tensor parallelism. And let's start with the pipeline parallelism. So instead of splitting the data in the data parallelism, pipeline parallelism splits the model. Like if your neural network has 8 layers, I can split layer 1 to GPU 1, layer 2 to GPU 2, layer 8 to GPU 8. And they get fed with the same piece of data and pass through a different part of the model. So if the total model size is 350 gigabytes, and I can use 8 GPUs, so I can have each GPU 1/8 of the total model size, which is 43 gigabytes. Although this is not quite accurate, since you have to also store those optimization states and also the gradient, so that's not necessarily mean it can exactly fit. So with pipeline parallelism, large models can be placed and trained on GPUs, especially when like large language model where each layer is homogeneous, the dimension is exactly the same for the weight, for the activation. It's relatively easy to maintain, to keep each GPU busy. What we don't want is that this is a pretty thin layer, pretty small layer. This is a pretty big layer. So this GPU will take super fast to finish, or it'll be idle to wait for GPU 1 to finish or GPU 3 to finish. So you want to make sure in each pipeline stage, the processing time for the GPU to process that layer or that group of layer is roughly the same, equally divide the training workload, which is good for large language model. Basically, you're stacking the same architecture on once and once again. So in pipeline parallelism, this is the training data flow. You start with layer 0, layer 1, so the forward pass, and then you do the backward pass. This is the training data flow. F0, 1, 2, 3, and then B, 3, 2, 1, 0. If we do pipeline parallelism, we can show the naive implementation on the right, where F means forward, B means backward, and 0, 1, 2, 3 means layer 0, 1, 2, 3. So we can do the forward in 4 GPUs. After GPU 0 finish, we handle it to GPU 1 and handle the layer 2 to GPU 2, handle layer 3 to GPU 3, and then backward, run it on the same GPU and then GPU 2 again. So this is an example training a 4-layer network with pipeline parallelism. What's the problem here? The GPUs are getting underutilized. Although we need to store only one-fourth, basically 1/4 of the weights, since I have 4 layers, but now each GPU is responsible for only 1 layer, both in the forward and also in the backward. But there's a lot of bubbles, a lot of idle time. So the GPUs are actually underutilized. After I calculate layer 0, I'm just idle. I have to wait a long number of cycles before I calculate the backward pass. Probably GPU 3 is okay because forward it immediately does the backward, but again, it has to wait a long time before it begins to work on another forward. Similar for GPU 1, it has to wait all this time here before it calculates backward. So the accelerators, the GPU is heavily underutilized using pipeline parallelism naively in this way. And how can we improve that? Actually, using this way, the utilization is only 25%, 1/4. Since if everything is busy, they should all have the rectangle. Right here, there's nothing. This is an improved approach. So basically, we split the batch into several micro batches. For example, if we have 16 images, and now we want to split it by 4 by 4 by 4 by 4. Okay? 4 chunks. Each chunk has 4 images. So that in this way, what I do here is that layer 0, GPU 0, will still be responsible for only layer 0, but it will consecutively calculate for batch 0, batch 1, batch 2, and batch 3. As soon as it finishes the compute for batch 0, it can handle it to layer 1. So GPU 1 starts to calculate the layer 1 of batch 0. And then the layer 1 of batch 2 of the second batch also finished. It can handle it to the layer 1. So that you can overlap the GPU 0 and GPU 1 in this case. In the previous case, GPU 0 and GPU 1, they completely operate at a different time. When GPU 0 is busy, GPU 1 is idle. Now they are overlapped by computing different batches on different, by computing different batches separately rather than everything together. So as soon as layer 1 is finished, it can handle the GPU 2 to compute on layer 2 for batch 0, batch 1, batch 3, 2, and batch 3. Until it finishes all the forward layer, this is the backward layer for layer 3, and then layer 2, batch 0, 1, 2, 3, again and again. Okay, so in this case, the batches are split into even smaller batches so that we can overlap different GPUs compute time. And let's see what is the improvement here. What is the new utilization? Previously, every 4 elements, you have only 1. So you have 4-layer neural network. Assume each layer require the same time for forward and backward. For example, there are a large language model where each layer is exactly the same architecture. So the utilization for this 4-layer neural net on 4 GPUs, the utilization is only 25%. Using the mini batch approach, assume each batch can finish exactly at the same time. The idle time is reduced. By counting the bubbles here, we can calculate the utilization considering the bubble have improved to 57%. It's about 2.5x improvement simply by mini batch. Okay, so the more chunks you have, the chunk means the number of micro batches. In this case, micro batch reduced from 16 to 4. The more micro batches you have, actually the higher the utilization. But what is the bad thing about it? When you have super small batch, that batch may not be able to occupy the whole GPU if the layer is pretty small. So that's the issue here. You cannot not go too small. So that's about pipeline parallelism and also how to improve the GPU utilization by further using micro batches. The last parallelization opportunity is by exploiting the tensor parallelism. So what is tensor parallelism? Unlike the pipeline parallelism that chops the different layers, we can chop in the dimension within a layer to make it more fine-grained. So for example, this is the weight of a layer. This is activation times weight, which is another layer. I can chop in the weight dimension. This is just one layer. Previously, we were chopping in different layers, but now we are chopping just one layer, but have three separate GPUs to calculate each part. And this is a single matrix multiplication. And we make sure we want to divide it in the dimension where there's no reduction so that we can reduce the amount of communication. And let's see a real-world example in this Megatron LLM, which is NVIDIA's very cool distributed training engine that can train multi-billion parameter large language models using model parallelism. And how do we use model parallelism to handle the MLP layers and also the self-attention layers, which is the building block in transformers and large language models these days. So tensor parallelism, the definition is that we want to split a weight tensor into n chunks and then process them at the same time across multiple GPUs. And here, F and G, in the figure here, F and G denotes the all reduce and identity operations to synchronize. And the parameters and activations in the blue part are sliced across different GPUs. In this case, we have two GPUs. So A is actually the first layer of MLP, the weight for the first layer. B is the weight for the second layer. In this example, we have two GPUs. And first, we divide the A matrix, the first weight matrix, in this direction, in the vertical dimension, and the B matrix in the horizontal direction, which can minimize the communication. Okay, since let's see actually an example. How do we partition? Why we partition alternatively, one in the column-wise and the other in the row-wise. So here, we are partitioning the column-wise. This is the first chunk on the GPU 1. This is second chunk on GPU 2. And blue is the weight. And the red is activation. This is one layer of the neural net. This is the 1 by 2 times 2 by 3 matrix. Okay, so 1 by 2 times 2 by 6. And 6 can be divided among two GPUs. Each one is responsible for only 3 in this case. Since this is a 2-layer neural network, the second layer, the weight dimension is 6 by 2. The first layer is partitioned in the column fashion. Okay, since you're in the column fashion, we don't have to do any reduce. We can calculate x times a1, x times a2 separately. There's no need to reduce, to do any reduction. So this is 1 by 2 by 2 by 3. So you get 1 by 3 in the end. You get y1 and y2, which is here, y1 and y2. They are completely independent. No reduction is needed. No communication is needed among these two GPUs. And so far, we completed the first layer of the MLP. What about the second layer? We have y1 and y2 right here. We chunk the second matrix in the row manner. Why do we do that? So that we can multiply y1, which has 1 by 3, with the first 3 rows. Okay, remember B1, B2, the B matrix is 6 by 2, and we are going to divide in the 6th dimension, the first dimension. Okay, so that y1 multiplied with b1 and y2 multiplied with b2, they share this dimension 3. In this case, we actually need to do all reduce because these are partial results. This is the full result, and this is the partial result. Therefore, we need to do all reduce in the very end to get the final z, which is 1 by 2. And in this way, we don't need to do any communication in the middle, but only do all reduce in the very end. And luckily, only the large language model only have 2 FFN layers, and that's exactly we can do the vertical separation and horizontal separation to handle that case. And the amazing part is there's no communication after the first layer in this method to chop in the horizontal, first vertical and then horizontal. What about the attention layer? The attention layer, we can chop it actually in this way. We have 2 GPUs in this case, GPU1 and GPU2, and then we have QKV matrix for query key and value. And let's see how do we do that. Actually, we can divide it using the head dimension. So this is head 1, this is head 2. Remember, we have this multi-head attention, MQA. So we can divide in the head dimension. GPU1 is responsible for head 1. GPU2 is responsible for head 2. So this is the QKV projection. We broadcast the original embedding into 3 GPUs and calculate the QKV projection for head 1. And this is the QKV projection for head 2. And then we get the projected QKV for head 1 on GPU1, head 2 on GPU2. And after that, we are going to do the QK transpose times V, which is the attention mechanism. So each head is done independently. So here we have 2 heads on GPU1 and GPU2. They are done separately on each GPU for QK transpose times V for head 1, QK transpose times V for head 2. There's no communication needed among different heads. And then we get the result for head 1 and head 2. And last step is the output projection. Okay, so we have moved from the beginning input projection, QKV projection, to this is the attention mechanism, and finally is the output projection, where multiple heads we finally need a reduction here. So this intermediate output, and then we need an output projection matrix that can blend different heads together. This is head 1, this is head 2, and then we multiply it with the output projection matrix that is going to blend the partial result into the total result. And the compute itself can be parallelized in GPU1, GPU2, get the partial result, and finally we do all reduce to sum them up into the final result before passing it to the FFN. And it's actually pretty amazing that there is no communication between the different nodes in this case, because different heads can compute the input projection independently. You can also compute the attention mechanism independently among different nodes. Only at the very end, when you need to, after the output projection matrix, you need to do a communication right here. Do a communication right here by doing such all reduce. Okay, so summary of today's lecture. We first talk about 3 different kinds of parallelism. Data parallelism, we split the data, same model, across different workers. Pipeline parallelism, we split the model in the layer dimension. And then the tensor parallelism, we split the model by the tensors inside a tensor. We also talk about several communication primitives, including the reduce, many to one, or reduce, many to many, and a very efficient method using this ring or reduce, and also recursive halving or reduce to reduce the communication bandwidth. Very importantly, we introduced 0, 1, 2, 3, and also fully sharded data parallelism to reduce the the GPU memory requirement by trading off to have more communication, to have less GPU memory by sharding the optimization state, not only optimizer state, but also the gradient, both the optimizer state gradient and also the weight to fit larger models. And finally, how to implement pipeline parallelism by using micro batches, and also the tensor parallelism for both the FFN layer and also the attention layer to minimize the communication. We'll be able to exploit the parallelism. So that's all for today's lecture. In the next lecture, we are going to talk about techniques to save the communication bandwidth and also how to tolerate the communication delay when you have limited amount of bandwidth and also high latency. And after the lecture, we're going to give you a lab tour to our server room. So that will be a pretty exciting lecture this Thursday. All right, that's all for today's lecture. Hope you have a good day.